And welcome to Climate Chat. I'm your host, Dan Miller, with my co-host, Leon Simons. And today we're doing the second in our Ask Us Anything series. The last one was about 6 months ago, and it actually was pretty popular. I mean, we really got a lot of good discussion going. And so today is a day, because very often at the end of an interview, we have questions, and then a lot of times those questions kind of branch off into different subjects, maybe not really directly related to the interview. So we don't really have a chance to address them. So today is that day. If you have questions, please, let me put it down here. If you have a question, please put it in the YouTube live chat and preface it by Q or question or something like that, so we can identify it's a question as opposed to just a general comment. We also ask people to put questions in X Twitter accounts and Bluesky accounts, and we have some from that there as well. And we might even just pick up on some other topics that came up on Twitter and things like that as we go along. So, and of course, in addition to asking questions, please like and subscribe. I guess on this channel, we don't nearly push that as much as other channels do. However, we're here to try to raise awareness of a very critical issue and to let people understand the where climate change really sits, as opposed to what you might hear about otherwise. And so it's important to get that message out. And the way we can do that is by you helping, by liking and subscribing. It's free to do, so nothing, no cost to you. And also share it with your friends who might be or should be interested in climate change. And let's try to grow the numbers so we can get this information out to more people. And by the way, I have a little bit of a cold today, so excuse me if I cough on air or something. I'll try to mute before that happens. Anyway, Leon, welcome.
Hi, thanks. Just getting some last questions in. The many questions came in at the end.
Okay, well, while you do that, I have a list here of some questions that were on the social media. And let's see. So one of them is this is from @Climate Messiah. Okay, there you go. The comparative forcing impact of a methane molecule to CO2 is frequently stated in terms of how much more warming it causes over long periods of time, like 20 years. It's actually usually 100 years. How much more warming does a methane molecule cause in the immediate term? And the answer to that is, while it is in the atmosphere, methane warms about 120 times as much as does CO2. Now, the big difference is that CO2 lasts in the atmosphere for hundreds to thousands of years, while a methane molecule lasts for about 12, 15, maybe 20 years. So that's why they do these 20 and 100-year things. So, but right now, the methane that is in the atmosphere is warming the Earth about 120 times. Now, how can we see this? Like, what are other ways of visualizing this? Well, it used to be that CO2 at the pre-industrial times was about 280 parts per million. So there are 280 CO2 molecules for every million air molecules. 280 parts per million. Now it's about 420, a little bit more, but around 420, and it's gone up 50%. So it's gone up 140 parts per million, 140 parts per million. CO2, on the other hand, was about 0.7 parts per million, 0.7 parts per million pre-industrial, and now it's about 1.9 parts per million. So round it off to 2 if you want. So, and if you look at the IPCC and you look at how much warming does CO2 cause versus methane, methane's about 2/3 or so the warming of CO2. Now, there's other greenhouse gases too that contribute to warming, and there's aerosols that contribute to cooling. But if we're just comparing CO2 and methane, you can say, roughly speaking, methane causes about 2/3 that of CO2. So, and the CO2 warming is caused by the 120 parts per million of 120 parts per million, excuse me, of CO2, and the methane warming is caused by the 1.2 parts per million of methane. So you can see that tiny bit of methane causes a lot more warming per unit than the CO2 does. And that's, methane is CH4. It has all these like wobbly hydrogen atoms. It's really easy for them to pick up infrared heat and then vibrate and then give off that energy in a different direction. Oh, here we go. Go ahead there.
Yeah, I think when we talk about it, I think it's always useful to sometimes go back to the basic physics here, and I think you could find this graph on Wikipedia. I think Robert Rode made it, or at least he made a similar graph as this, and yeah, you see these are wavelengths of radiation, and this, of course, the sun radiates heat to Earth, and that happens at a certain temperature, and that the surface of the sun has a temperature of about 5,500 degrees Kelvin, which is a bit. So you add about 270. You reduce it by about 273 degrees Celsius to get Celsius. So because at that temperature it radiates at a certain wavelength, and of course these wavelengths we consider those visible light, and you can see if you have a prisma, you can see these different wavelengths of light visualized by these different colors of light, of course. So we know, of course, I think most people have some feeling about different wavelengths of visible light from the sun, but there's also different wavelengths of infrared light. And the Earth has a temperature of about 15 degrees Celsius. So in Kelvin, you can see that the Earth radiates at a different wavelength, of course, than the sun. And we don't see our eyes cannot see infrared light, which is invisible to us. But this radiation, of course, is real, and we can measure it, and we can see that certain radiation goes through the atmosphere more easily than other wavelengths of infrared radiation, and it's caused and that's mainly because water vapor absorbs certain wavelengths of infrared radiation, but there's also certain windows, especially here, where water vapor doesn't absorb all the infrared radiation, but carbon dioxide, for example, does. And then to go to the methane, so methane absorbs, again, different wavelengths of infrared radiation than carbon dioxide does. So especially within certain parts of these windows, more radiation is absorbed than would be absorbed without the added methane into the atmosphere, and without the added CO2 in the atmosphere. So that's also one of the reasons why it's important that these different greenhouse gases have different effects. And
Okay.
to get another question about this, I just included it here, was I would like to know what's behind the extreme peak in methane at the moment. So yeah, then we have this graph from a recent study. I didn't include the title here, but you can see, of course, there was an increase in methane and then there was a certain equilibrium. So the amount of methane emissions and the reduction in methane by hydroxyls. So these are these radicals that reduce methane. They interact with methane, and then the methane is turned into the carbon of the methane is turned to CO2, and the water is turned to water vapor. So there was at a certain point that there seemed to be this equilibrium reached between the emissions and the reaction in the atmosphere with hydroxyl. But then it started to increase again, and then now the growth has accelerated. Last year seems to have decreased a bit again, but the question is, so why is it peaking? And it seems that, of course, there's an increase in emissions from industry, especially with fracking. So there's more methane being there's more drilling for methane, and then the transportation of this methane through pipelines and through shipping also releases methane to the atmosphere. So this is one of the explanations, but also an explanation is that the biosphere, so the land, is producing more methane because of CO2 fertilization, because of an increase in warming, more rainfall, so more water produces more methane because of anaerobic combustion. So the carbohydrates, so the biomass is turned into methane rather than CO2 if there's less oxygen available. And as we talked about here in the past, it can also be partially be explained because there's a reduction in sulfur. Because if there's less sulfur, there will be more methane being produced by these different microbes. So we have a whole talk about that on Climate Chat as well.
So by the way, so let's keep talking about methane versus CO2, and just you're giving sort of a detailed explanation. I'll try to give a higher level, sort of just how you can kind of simply understand it. But I also want to point out that on your chart, it shows like the top is 1900, and I mentioned it's 1.9. So this is parts per billion on the left side there. And 1900 parts per billion is equal to 1.9 parts per million. So because methane is so much more powerful than CO2, they actually use a different measure. They use parts per billion to keep track of it instead of parts per million. Excuse me. And then the other thing just to think about, why is methane versus CO2? Before we look at that, let's say most of the atmosphere is oxygen and nitrogen, O2 and N2. So why aren't they trapping heat? And the reason is that's two atoms joined together, and they have a very strong bond, and they don't sort of vibrate very much. I mean, they're not floppy, is one way to think about it. But when you have a CO2, you have a carbon atom with two oxygen atoms hanging off, and those oxygen atoms can kind of bounce around when it's hit by infrared radiation, and then it can re-emit it. So it's sort of so you need to have sort of 3 or 4 atoms or more to make it work as a greenhouse gas. And then methane, CH4, is a carbon atom with 4 hydrogen atoms around it, and that's very floppy. You can kind of think of it, like think of those bonds as springs, and then they just kind of bounce all over the place. And so it's better at picking up heat. I know that sounds very unprofessional, but that's a way a scientist once explained it to me, and I thought that was a great way to understand it. And let's talk about some myths that come up with this chart. In fact, you'll hear climate deniers say, "Oh, the CO2 effect is saturated," and they're trying to say it doesn't matter if you put more CO2 up; it won't cause more warming. And first of all, it's just not true. And they also claim that water vapor is the whole thing for warming, and therefore CO2 has no effect. And that's also not true, as Leon explained already. And also, it is the warming from CO2 which causes more water vapor to go into the atmosphere and cause more warming. So the water vapor is actually an amplifier of CO2 warming, as opposed to
it's a feedback. We call it indeed an amplifying feedback. So as you see, water vapor absorbs a lot of radiation. So if you have warming and the atmosphere, when it warms, it can hold about 7%. The atmosphere can hold 7% more water vapor for every degree Celsius of temperature increase. So that's exponential. Many talk about exponentials without knowing what that means, but that really means it's exponential. The atmosphere can hold exponentially more every degree Celsius can hold 7% more water vapor. So then and you can see it in the tropics, especially when it rains, it pours, right? If you have to, once this air, this tropical, really warm, moist air cools down, you have these enormous downpours, because you have this condensation happening, and then because this warm air can hold so much water, there's also much more water that can come down when it starts raining. And indeed, then if there's much more water vapor because there's warming, that's the strongest, or one of the strongest enforcing feedbacks there is, next to clouds cover. So with warming, there's less cloud cover, but I think we'll get to that later. Okay, I think there's a lot of questions to cover.
Yeah, I guess we could probably spend a whole hour talking about CO2 and methane, but I think that's just useful. The other one is just to understand. I do have a video. It's available on the Climate Chat website, and it's called CO2 Ink Demonstration, and it shows, excuse me, how things in very small quantities can have big impacts. And basically, I put 280 parts per million of ink into water, and you can see how dark it gets. And then I go up to, back then, I think it was 380 when I made that video, and now it's a lot higher now. But anyway, it's an example of why things in very, very tiny amounts. And the bottom line reason, even though we could go into more detail, it doesn't matter what the percent is of something. It matters how much it is. And in this case, we went from 2 trillion tons of CO2 to 3 trillion tons of CO2. And 2 trillion tons was sort of the sweet spot for the Holocene and keeping the climate the right amount. When we increase it by 50%, that's not very good. So that's the super short version. All right, let's. There's a lot of good questions in the chat already. So
yeah, I think I included some here.
Okay.
I just want to give a short notice about this. So here's the methane. Go back to the methane. So you see, really, this methane has really, compared to the past 800,000 years, it's really the increase is really enormous, and it's hard to tell when the last time was methane concentrations were this high. Potentially about over 40 million years ago during the Paleocene Eocene thermal maximum, but we really don't know. It's and at least it hasn't been for the past 800,000 years, because that's when we have these ice core data available. And this is really a great graph, but it was on the Environmental Protection Agency, the US EPA website, but they took it off. They took the climate indicators web page offline. And I secured these slides and these data sets on GitHub, where you can find it if you search for it. So you can find the data from both from methane and from N2O, nitrous oxide, and from CO2 for the past 800,000 years, and the slides that go with that.
The good news is, when you get rid of the information, when you stop posting information about the dangers of climate change, the dangers go away and they don't exist anymore. So that's the good news. So the government's doing us all a favor here by getting rid of this information here.
Yeah,
maybe not.
Okay. I think that, so happy 10-year anniversary for the Paris Agreement, everyone.
Yeah, but it's doing a great job keeping those temperatures down.
Yeah, so that's what this question is about. You've probably already answered this, but the Paris Agreement says to limit global warming to 1.5 degrees Celsius, greenhouse gas emissions must peak before 2025 at the latest and decline by 43% by 2030. Is Paris dead, given that we've probably surpassed 1.5 degrees already? And then a question about the increasing ambitious climate action, right? So yeah, here I made this like 3-year average to reduce a bit the natural variability of everything. A graph both from NASA in blue and the ECMWF Era 5 data set, and you can see that indeed NASA isn't there yet, but almost reaching for a 3-year average of 1.5 degrees Celsius above these pre-industrial baselines. And here for NASA, I use 1880 to 1920 because that's what James Hansen uses, and it's analogous to the pre-industrial baseline. And ECMWF uses 1850 to 1900, and you see these agree quite well with one another. With ECMWF increasing a bit more recently, but yeah, it's. I think that this is.
Wait, check out. Look what happened in 2015. That was the Paris Accord. The 2015, right there. It's like right between the two of us. There, it was 2015. It looks like the Paris Accord caused the rapid increase in warming.
Yeah,
right?
exactly. So
and then boom, temperature shot up. Now, keep in mind, I think it's important to say, and of course we bring it up on this show all the time.
You cannot
Paris
see it.
Accord, all these numbers, these predictions. Well, these are not predictions. This is actually the measurements, but the predictions of the future and the carbon budgets that we need to stay under in order to stay safe and stay under 1.5. All of that is based on IPCC models that generally, and it's hard to say, have a central estimate of 3 degrees warming for a doubling of CO2, called the equilibrium climate sensitivity. As we've been talking about on this show a lot, James Hansen, one of the most prominent climate scientists in the world, Leon worked with him on this very famous paper, Global Warming in the Pipeline, which went into this issue. Hansen says, using multiple lines of evidence. So this is not like this one thing tells us. There's 4 different ways you can come about this, that realize that the ECS, the climate sensitivity, is actually 4.5 degrees. In other words, for a doubling of CO2 after the short-term impacts, which actually could take 1,000 years, but the short-term impacts happen, you'll have 4.5 degrees of warming instead of 3 degrees of warming. That's a 50% increase. That obviously screws up everything we're talking about here. In other words, if you just follow the Paris Accord, and Hansen's right, and I do think he's right, then you're going to blow through the numbers that they were saying. Don't blow through. And we've talked about it so much. I don't want to get in like heavy duty detail of why this is and how it's offset by aerosols. But just keep in mind, whenever you see an IPCC report or anything like the official stuff, they are not factoring in this new research that shows that the equilibrium climate sensitivity is actually much higher. And what that means is that there is more global warming in the pipeline, which is why the paper was titled that. So I don't know. We could go down that rabbit hole, but maybe I'll just leave it at that.
Yeah, I think we discussed it recently, but we had this meeting in the Netherlands here in with many of these large agencies where we were talking about 10 years after Paris, and the introduction was also like that there's some reason for optimism because we've avoided the worst and we will keep warming below 2.6 degrees Celsius. But that's really wrong, and I talked about with some people about it. But it's quite crazy that this number is now out there, and it's in a way it seems to be connected to this message that we've passed 1.5 degrees for all intents and purposes, and then that many think there should be some hope attached to that message that we're not doomed or something, and that we keep warming below a certain level by avoiding some most extreme scenario, which wasn't never possible anyway, right? But indeed, this 2.6 degrees. It's what is it based on? If you try to understand it, it's almost impossible to see the underlying assumptions of other greenhouse gases like methane. We talked about it. What are the assumptions of methane? They talk about CO2, but they don't show what their assumptions are on methane for the coming 75 years to get to the point, right? Or they don't share their assumptions on aerosols. So if the aerosols reduce and CO2 keeps increasing and methane keep increasing, even if the climate sensitivity is not higher, which is most likely is, then the warming will also be much higher, even with ambitious reduction scenario, which CO2 emission reductions. But again, those plans or those commitments are only that. We don't see it turn into action yet. We don't see the emissions going down yet. So yeah, you can solemnly swear that you do anything, but if you're up to no good, right? In the end, it's actions that count. So I think that's also important to note. And during this meeting, maybe we can now show the video then.
Okay.
Yeah, during the video, during the meeting, someone talked. I didn't get his name, but someone talked about this paradox. I thought it was quite interesting because we see a lot of this during this meeting, but we see it online also, and almost every media article has to finish with this like sliver of hope, and often it's false hope, right? I think hope is fine, but I think false hope is not fine. And someone talked to me about this, and I looked it up, and this video really explains that.
Okay, and it's 3 minutes long, everyone. Just
I would like to give you a way of thinking that has been enormously helpful to me, that came from the Good to Great research for dealing with great difficulty. And it was what we came to call the Stockdale paradox. And the Stockdale paradox was taught to us by, when we were doing the Good to Great research, we're trying to make sense of the CEOs. And in doing that, I just by chance happened to get to know Admiral Jim Stockdale, who was the highest ranking military officer in the Hanoi Hilton, shot down in 1967, was there till 1974. They could pull him out at any time and torture him, and they did. He tortured over 20 times. And I had the privilege to get to know Admiral Stockdale, and we were going to the faculty club one day, and I had read his book, In Love and War, which was written in alternating chapters by himself and his wife about their years when he was in the camp. And I got depressed reading the book because it seemed so bleak, it seemed so difficult, it seemed, it's like we can all endure anything if we know it's going to come to an end and we know when. But what if you don't know if it's ever going to come to an end? And you certainly don't know when. So I asked Admiral Stockdale how he dealt with that, and he said, you have to realize I never got depressed because I never, ever wavered in my faith that not only I would get out, but I would turn being in the camp into the defining event of my life that in retrospect I would not trade. Later, when we were up the hill, I asked him, I said, Admiral Stockdale, who didn't make it out as strong as you? And he said, easy, it was the optimists. I said, the optimists? You sounded optimistic. He said, no, I was not optimistic. I never wavered in my faith that I would prevail in the end, but I was not optimistic. I said, what's the difference? Well, the optimists always thought we'd be out by Christmas. Of course, Christmas would come and it would go. And then we were going to be out by Easter and Thanksgiving, and then Christmas would come again, and they died of a broken heart. And that's when Admiral Stockdale grabbed me by the shoulders and said, this is what I learned. When you're imprisoned by great calamity, by great difficulty, by great uncertainty, you have to, on the one hand, never confuse the need for unwavering faith that you will find a way to prevail in the end, with, on the other hand, the discipline to confront the most brutal facts we actually face. And we're not getting out of here by Christmas.
Okay, and by the way, we should point out the Hanoi, for those who don't know, the Hanoi Hilton was the prisoner of war camp during the Vietnam War. So Stockdale was a prisoner of war, and the North Vietnamese tortured him. That's what he was referring to there. Okay. Let's see. Can we turn off this other thing here? And let's see. So anyway, I have a few thoughts on that. I think it is useful in some ways. My feeling is slightly different. I'm very optimistic that we can prevail eventually, but not necessarily that we will prevail. It's up to us. And we talk about here often, like we're choosing to fail, right? We're not actually doing much of anything yet to fight climate change. We're trying to give people information here about the dangers of climate change and the solutions as well. And at any time, we can choose to succeed. Now, that doesn't mean we're going to avoid the calamity. For example, sea level rise will probably continue for centuries or millennia, even if we all of a sudden decide to stop emitting. Well, certainly if we stop emitting carbon and that's all we do, then the sea level will go up. The last time CO2 was this high, the sea levels were about 75 feet higher than they are now. And that's where we would continue to head if all we did was reduce our emissions. But there's other things we can do. And we'll probably talk about that later. But I just want to say that to me, it's not like we're going to win no matter what. We're going to win if we finally decide to actually take action, serious action.
Yeah,
not just.
Yeah, I think that's the message I take from it. I also I think I live by is that the point that we need the discipline to confront the most brutal facts we actually face, right? I think that was really an important part of the message, where because if we have this if we downplay the real risks, if we sugarcoat it, and for example with these aerosols, right? If we don't talk about this very inconvenient truth that when you reduce air pollution, that will lead to more warming, right? Well, that's a fact, and that's the main driver of regional warming. We see that now in Europe, which is the warmest continent, as we clean up our air pollution. Mm-hmm. If we don't talk about it, and the models don't take that into account, we have much more sunlight, so that's good for solar panels. Well, we see the wind decrease, and so we invest billions, and globally hundreds of billions every year in flood defenses, in infrastructure, in energy systems that are not fit for the reality that we will have over the decades ahead, right? So mm-hmm. It's really also a financial. We have a strong financial incentive, and of course, environmental incentive and a social incentive to take reality into account and to face the truth head on, and not to sugarcoat and not to lie to people, because that's often in what's happening, right? People are being lied to, maybe not always intentionally, but often also intentionally, because they
don't want to be. People don't want to be, sound like a doomer. They don't want to hurt. I mean, look, we've had many people on the show talking about climate communications and that debate versus hope versus fear, right? They don't want to. Don't have a scary message, because that will turn people off. What? It's exactly the opposite. It's the number one motivator is fear, right? Hunger, sex, and fear, right? Or big motivators. And I think the other way. Okay, let's say you give me a really hopeful message. What's my incentive to act? You just said things are going to be okay. So why do I have to really go out of my way to change things if everything's going to be okay? And so far, by the way, of course, I talk about climate change all the time with everybody I meet, of course, and it's not always appreciated. But I will tell you that most people that I just run into that are, again, smart people, educated people, whatever, in the know about many things, they don't know what's going on with climate. I mean, they know climate's a bad thing, and you could tell they're pushing it out of their mind. And then when I bring it up, by the way, it's way worse than you've been told, and I go into that a little bit. You can just see, they don't really want to talk about it anymore.
And it's inconvenient.
Back to just ignoring it. So that's I think I've said it many times. We know all the science we need to know about climate change. We're going to learn more, and that'll be good. But we know all we need to know to act. And we also have all the tools we need to act now. We're going to get more, and they'll be better and cheaper and at scale and all that kind of stuff later, but we can get started right now. So the only thing that's stopping us, it's not the science and it's not the solutions. It's it's our brains, the fact that humans are really bad at looking at long-term problems, right? We just react, that's how we evolved to survive. It's just to focus on short-term threats, but not to look at long-term threats. And so
I think that the other part of the Stockdale paradox, where he knows that those who didn't make it, or who didn't make it out, or who died, or who got really, like, I think in a way, like the what do you call the post-traumatic stress, or PTSD. Those were the people who thought they were getting out by Christmas, right? Who had this like false hope, and I see it also with many people in the climate community, but also, for example, with medical issues, for example, cancer, where people they grasp to this false hope, or whether it's these snake oil salesmen that say they can cure cancer, or whether it's snake oil salesmen that say that we can still keep global warming by 1.5 degrees, right? That causes people to grasp to this hope, and of course, like, they cannot cure cancer, right? Or we cannot keep warming below 1.5 degrees Celsius. So then people who are grasping to this hope, they get depressed because they thought they've been lied to. They've been sold this false hope, and it happens again and again. Right now, it's like we're passing 1.5, or we'll keep global warming below 2.6 in 2100. But then within the next 10-20 years, when we'll reach 2 degrees, right? People they will experience again this like shock that they've been lied to again, and that's what's happened, right? We will face this more and more of these extremes, which people are not preparing for. Mm-hmm. So it's not just this emotional thing that they thought they wouldn't have so many problems, but they are having more problems. But it's the infrastructure that will be having these problems, because we are not making these investments that are needed for these rapid changes that are already.
You can't, 10-15 inches of rain in 24 hours, you're not going to build a sewer system that's going to handle that. 3 inches. Sure, but 3 inches is hard to handle, let alone 10-15. So yeah.
Okay, so more questions. I think
we could. It's easy to spend an hour on each question, so let's try to get through a bunch more. I have more, but
I think that we can build on these, right? I think Nadia here asked, are temperature deltas really good way to characterize climate changes? And then she's relating to these global mean surface temperatures. So I think are precipitation patterns and heat extremes the most directly consequential aspects? And I think that's starting off with this graph by Makiko Sato. And we talked about this more often. I think this shows indeed, and you see all these maps where you see that global warming doesn't, like, there's no global average temperature increase, right? That ocean warming, global warming is mainly ocean warming, because the oceans take up 90% of the heat, and then you see that the heat is distributed not evenly across the globe. And we talked about these northern hemisphere mid-latitudes, where you see, especially after 2020, this enormous increase in warming, and we call this like a new permanent El Nino-like temperature increase, right, over the northern hemisphere mid-latitudes. Yeah. And that's really what influences, of course, very much also the weather of the northern hemisphere mid-latitudes, right?
By the way, I think a lot of people won't understand what these graphs are. Let me just quickly highlight what's going on here. The upper left graph, showing two different color lines, is showing ocean surface temperature, and the blue line is the northern hemisphere, and the the red line actually is the center, right? 20
the tropics.
to 20 is the tropics. It's like around plus or minus around the equator.
This region.
And showing how the ocean temperature is rising at different rates depending on where it is in the globe. That's one thing. The chart below it is kind of hard to understand, but it's really cool once you do understand it. What it shows is the y-axis is the latitude, and so the bottom is like minus 60, and then the very bottom would be Antarctica, and the top is the North Pole. But what it shows is it's combining all of the oceans at that latitude into one point, and then the x-axis is time. So it's showing how the ocean at every latitude is warming over time, and then you see some in the middle there. You see an El Nino where it gets dark red. Hold on a second. Whoop. Sorry, I can't talk.
Yeah. So you see these El Ninos, these tropicals, those dark colors and the pink colors. You see, it is a 2015 to 2016 Super El Nino, which you see from the global tropics, oceans. You see that there's this spike. You see it again here in 2023, 2024. You saw this other spike.
Okay.
Yeah, and then here you see from 2020 onwards, you see that these colors are starting to show up to these monthly data points, right? Are starting to show up over the northern hemisphere mid latitudes more and more.
Mm-hmm. And then on the right side, it just shows the maps of the world showing ocean temperatures and how
the different years.
Yeah, and different years, and just show that some places it's hotter than others. So yes, the 1.5 degree number is this global average surface temperature. By the way, surface means 2 meters above the surface. If you actually measure the temperature of like black asphalt, it could be way hotter than it is. But so sort of where your head is located above the earth, and that's the temperature, and that's above the ocean and the land. And the land tends to be warmer than the ocean. And so the average land temperature is more than 1.5 right now, and the average ocean temperature is below that. But it is a useful single figure to keep track of where we're at, and it then indicates danger levels where you might trigger tipping points. I think that part of the question as well.
Yeah,
points that might be triggered, and so
yeah, I think we'll get to that later. But I think. Yeah, let me cover this. So again, you see these latitudes, we talked about it in detail. So where this radiant absorbed sunlight and outgoing long wave radiation, you see this imbalance increase over these, especially over the shipping region. So more heat is accumulating in the system, and then I just want to point out one more thing because I think this also really can impact the weather of North America, the west coast of North America. And this is the Pacific Decadal Oscillation. So this was another question by this climate science nerd who asked, when do you think the PDO, which means the Pacific Decadal Oscillation, will turn positive, further or even still faster increase global surface temperature? And that's where we get this graph, right? It showed you this northern hemisphere mid-latitudes but here's just the North Pacific, and the temperature and also how much sunlight is absorbed by the North Pacific. Before 2020, it was very much impacted by this Pacific Decadal Oscillation, which is this cycle of temperatures over the North Pacific and over the different parts of the Pacific. And you see this was quite in line, but then after 2020, it decreased and it went strongly negative, right? It hasn't been this negative. So these are 4-year averages to reduce this variability, but it hasn't been this negative, I think, for since 1850. But still, the level of absorbed sunlight keeps increasing. It has almost reached 5 watts per square meter over this entire region of 37 million square kilometers, right? So, and there's some, of course, there's a temperature increase. This region warmed more over the past 15 years than over the preceding 150 years. So that, but so the, and because of the temperature increase, you have more outgoing infrared radiation. Even while the greenhouse gases and the water vapor in the atmosphere are increasing, because it's very strong feedback of which is called the Planck feedback, that when a surface temperature increases, it radiates more heat. But that hasn't catch up yet with the strong increase in how much sunlight is being absorbed by this region, because less sunlight is reflected back to space. And it's now record high, right? It's I don't have this graph here, but you can see it here as well. So this imbalance is now record high. So the net flux increase. So much more heat is still accumulating in this region. So we will see much more heat, much more warming in the pipeline regionally, but also globally for at least this decade. And we don't know what happens in the future. But if this Pacific decadal oscillation increases, well, turns positive again, I don't know if that will happen. It might be also because I think it's related also in a way to these decreased aerosols that it's now this negative, because there was a very strong correlation until 2020. But if it turns positive, I am afraid that this black line, so the amount of absorbed sunlight, might increase much more, because there's still a lot of cloud cover over this region. There's still a lot of, this is one of the most, the region of the world with the most clouds, the North Pacific, because it's relatively cold, and so there's a lot of condensation happening, and so there's a lot of cloud cover. And if this warms, you have this feedback of warming, and then the clouds evaporate. So I'm very worried that this could really see a very strong spike, and it will be very much off the chart here. And then, of course, that will impact the weather across the globe.
Because let me ask you a basic question, which I think is probably other people have sort of asked in different ways in the comments already. And do current climate models reflect what you're showing here now? So this is data. This is measured data. It's not a model, but models are supposed to predict how much warming there is in different parts of the globe and everything like that. And if they're doing a good job, they're showing this increase in absorbed radiation and decrease in outgoing radiation. So are they doing a good job of this right now?
Yeah, I think I've been quite surprised by different model studies, right? Because so if you look at, if you're asking about this Pacific decadal oscillation, so the consensus, as far as consensus exists in science, was that when the Pacific decadal oscillation turns negative, the Earth's energy imbalance will decrease. But the opposite has happened, and of course we estimate that that's largely due to these, of course, continuous greenhouse gas emissions, but also very much due to reduction in aerosols, because that's what, of course, the data shows a very strong fingerprint from this increase in absorbed sunlight, right? And then, of course, the associated feedbacks. But if you're asking mainly about shipping, right?
No, I'm not asking about climate models, like IPCC climate models.
So climate models, of course, are a very important aspect of this, of climate models, is aerosols. And if you have these global average models, those don't do a very good job at understanding these regional changes. But if you want to understand these regional forcing changes, so like these shipping aerosol reductions, what we saw was before 2020, and so, for example, in 2013 or 2007, and there were these studies showing a very strong expected impact of these aerosols. So when you reduce these aerosols, we would see much more warming. So but after 2020, there's many of the studies show a very small effect. So there was a blog written that's showing these simple climate models based on FAIR, and you see many of these other studies showing a very small effect, but those are mainly based on simple on models, and they don't explain why they are much lower. They don't show their underlying assumptions why they are, and they don't agree again with the data. And then when James Hansen published earlier this year a study where they show a very strong impact of these shipping emission reductions, about 0.5 watts per square meter. That didn't get much attention, and many say, okay, that's an outlier, but that's an outlier based on observations rather than on models. So I don't understand why these recent studies are much lower than earlier models, and they also, while the observations show much stronger effect. I've been wondering about
isn't the answer that the models are not doing a good job of reflecting the reality of what we're measuring right now? Isn't that I mean, it's a yes or no question.
But what? That apparently. But then the question is why. So why?
Yeah.
And I can fill it in. I can say, okay, maybe they don't. They assume that that there are more aerosols from nature where these shipping aerosols are competing with, or maybe they just take a global average and they don't take into account where these aerosols are being emitted, or they don't take ocean warming into account. That's also, and then there's always this, like, is it a feedback or a forcing? That's a more an academic discussion. But yeah, I think we should go to the next question, because we've talked about it a lot, and this is what you were asking about this. So the basin of attraction, I think this relates to these tipping points. So when you have these like stable states, right? And we are now, of course, the Holocene, and we're now like more in the Anthropocene, has been very stable. So we had so this is the system state, and this is the control variable. But so this is like the stable Holocene temperature. But we are tipping over this the point where we're heading into a very warm period, right? And with very unknown, which is very unknown and likely very unstable, because we are entering a warm state of the climate where normally ice sheets don't exist, right? Because when the Earth is 3 or 5 degrees warmer, the Greenland ice sheet doesn't exist. So we'll see melting of the Greenland ice sheet. We will see all these tipping points happening associated with entering this new state. And we are already with 1.5. This is about the point, right, where we entering into this new system where the Greenland ice sheet will most likely melt, and the West Antarctic ice sheet will most likely melt, and the Amazon rainforest is under threat, especially also combined with the deforestation happening there. So I think we are reaching this point.
Okay. Yeah, well, and I guess the question was, is temperature the best measure versus things like precipitation? I mean, precipitation, of course, is very regional, and you probably wouldn't, even if rainstorm, like for example, United States, average precipitation hasn't changed very much, but in the eastern United States, it has gone up, and in the western, it's gone down. And then even in the places where it's gone up, it's much more intense. So it's really hard to have a single number for precipitation that tells us what's going on. Temperature is really not a bad measure, because it's the thing that pushes these other systems. Higher temperature means more water vapor can be held in the atmosphere. It's like a bigger sponge, as Daniel Swain told us, and it can rain more when it's a bigger sponge. It's also, when it's warmer, it evaporates moisture from the soil faster. So it makes droughts stronger, not just because there's less rain, but because more water moisture from the soil is being evaporated into the atmosphere. So all of those things are happening, and they're all kind of caused by temperature. So I think it is a good measure. The thing is,
it's one of the indicators.
Another one of the questions is that 1.5 degrees, 2 degrees doesn't sound very dangerous. I mean, you can have a swing of several degrees Celsius day to day, and it'd be totally normal day. But we're talking about global average temperatures, and therefore, it makes a really big difference. And think of it more like your body temperature. If your body temperature, I don't know what it is in Celsius, but 97.8 or something is the normal temperature in Fahrenheit. And you go up a few degrees, you feel bad, and maybe you're sick. You go up a few more degrees, you're dead. It's not like you can have a wide range of acceptable temperatures like that. So let's see. Maybe we should go to the next question. Again, I have some, but you seem to have a whole bunch of. Do you want to keep going or what?
Yeah, I think my camera switched to my other camera. I've been looking at ocean heat content. I think this was a bit related to the other questions. From 0 to 700 meters deeper, and I don't see clear visual acceleration. I think that's also an important point, like visual acceleration. I think that's, I don't know if Brian here did the assessment, but I think that's always important, right? Because eyeballing graphs doesn't teach you very much. More persistent, steady rise with less variability. From your perspective, do you see any robust evidence of acceleration in ocean heat content yet, or is persistence the better description at this point? And I think that's, we did the science, and there's those who have actually done the science assessing ocean heat content and really understand it. Those show that there's a very strong acceleration in global ocean heat uptake, including some who are very skeptical and cherry picking data sets. Now they do show acceleration in ocean heat uptake. And what's important to realize there, and let me show this graph here. I can understand his confusion, right? This is 700 meters. But what you need to realize if you want to understand ocean heat content is that data before 2005 is much less reliable than data since 2005, because we only have global observation system, or near global, right? With these 4,000 Argo floats, they're called, around the world, where they measured ocean temperature up to a depth of 2,000 meters deep. But even then, we don't have data from higher latitudes, and we don't have data from oceans that are less deep, from 0 to 300 meters deep. So there's a lot of uncertainty, and everyone studying this knows that. They know that we need longer time data sets, and you need to look at from 2005 to now. The data tells a different story and is more reliable than everything before that. So you need these different indicators to understand what's happening, and you need to be aware that if much of the heat goes to, for example, to the higher latitudes above 60 degrees north or below 60 degrees south, and you're not measuring there, or it goes below 2,000 meters, then you don't see this heat. So there's, for example, one other line of evidence is satellite data, where you see how high the oceans are with satellites, and you have global coverage of how much the sea level rises globally. And that's also an important indicator, because that means also how much heat goes into the ocean. As the ocean expands, if the ocean heats up, the ocean expands, and it takes about 50 times as much heat to expand the ocean from thermal expansion than from melting of land ice. So it's also, you need to understand those as well to understand. And so all these indicators combined. So we look at all these lines of evidence, and then you see that here you see this acceleration happening since 2005. And here as well, we see it happening since 2005. But really need, and if you look at the satellite data, you also see this acceleration happening in watts per square meter. So there's a fast increase in how much heat accumulates in the system.
Okay.
Yeah. So,
all right.
If you combine all these different lines of evidence, yes, we do see a very strong increase in the rate of global heat uptake, more than a doubling, and that's a peer-reviewed scientific study show that there's a more than a doubling in the rate of heat uptake over the past 20 or so years.
Okay, we have another related question here. What's the current rate of change of global temperatures in degrees C per decade? And I think the quick answer is, I think from 1970s to 2010, it was about 0.18 degrees Celsius per decade. And now it appears to be going around double that, 0.36 or so per decade. And that's also in your global warming in the pipeline paper, right?
Or maybe even more, right? That's this study. So indeed, the global warming in the pipeline paper was where we show about a doubling. We estimated about a doubling based on the evidence we had at that time. So about an increase of about 50 to 100% of the rate of global warming, which will be about close to 0.4 degrees Celsius. But now the Earth's energy imbalance has increased further. And of course, it might decrease again, but as the Earth's energy imbalance has more than doubled, it shouldn't be very surprising that the rate of global temperature increase has more than doubled. And that's if you correct for the natural variability of volcanoes and of the sun and of El Nino, then Grant Foster and Stephen Ramsdorff estimate this rate of warming of 0.43 degrees Celsius per decade. So it might decrease, but it might also increase further than this. So yeah, and that's also why we could reach this these 3 degrees by 2050, right? Based on the observations. Again, here this geodetic satellite, which uses this looks at these global sea levels, and these are the NASA satellites, series satellites, which look at these different wavelengths of radiation. And these are the models. So since 2005, from 2005 to 2023, those are much lower than these lines of satellite based observations. So that's why we really should take serious the potential of reaching 3 degrees by 2050, as the German Meteorological and Physical Societies warn that is a possibility that we could reach 3 degrees already by 2050 based on the observations, right? Not based on models. Also based on models, it's very unlikely. But if you combine these observations with the models, then it becomes more and more likely.
Okay. And let's, we have a whole bunch. Maybe we should try to get through quickly. Just give quick answers to some of these. Does CO2 really take 20 years in the atmosphere to reach its maximum greenhouse heating effect? Or are there studies at all about keeping the little mistresses living in luxury hotel? I don't know what that means. But the bottom line is when you put CO2 into the atmosphere, that's a forcing, right? You've done something to increase the temperature, but you don't see all of that temperature right away. You get that temperature from what you did, and then you get the feedbacks from doing that. And those feedbacks increase the temperature. So a quick way of thinking about it, when you do something like put more CO2 in the atmosphere, you get about a third of the impact, third of the warming happens in the first 10 years. The next third happens over the next 100 years, and the final third happens over the next 1,000 years. But it does take, a while. And we're seeing that with the ship emissions. It was an abrupt change of all of a sudden, instead of this case, warming, in this case, and this is warming because we reduced the cooling. And it didn't just happen 1 year, go up and stop. We're continuing to see it maintain that warming over several years so far. And that's because it does take a while for these feedbacks to kick in. So I think that's the fast answer to that.
Yeah. I think what's important also to note is that it takes much, like a global CO2 forcing is not really directly translatable to an aerosol forcing over the oceans, because the oceans take up 90% of the heat, and so they are the main heat sink. And if you increase the forcing only over the main heat sink, which takes a lot of heat to warm, so it takes about 4 kilojoules of heat to increase the temperature of a liter of water by 1 degree Celsius, then you can do all this math, and of course we've done all this math, and then if you understand that, and also, for example, if you look at, for example, the Mediterranean, if you heat up the Mediterranean, that heat doesn't stay at the surface, because it's more salty, so it goes to about 1,000 meters deep in the Atlantic. So so you need to really understand where this heat goes, and how long it takes for this heat to accumulate, and then if the climate sensitivity is higher, it likely takes longer for these points to be reached. So it takes more than 10 or 20 years for the first 30% of warming to be reached if the climate sensitivity is higher. But we don't know that for sure. So there's a lot of uncertainties, because then, of course, the Earth's energy imbalance has to match this increase.
But I think that what's important is when we talk about CO2, CO2 is a well-mixed gas. So when you put it in the atmosphere, eventually it just gets into the atmosphere everywhere, over land and over ocean. And so that number I gave, about a third in 10 years, a third in 100, and a third in 1,000 years, really applies to that and this global system. What you're saying is the cooling from ships is actually regional. It's actually mostly where the ships are, and cooling that part of the ocean. When you all of a sudden take it away, you're warming just that part of the ocean as opposed to the whole globe. And you said the oceans are great at absorbing heat. So the timing on how long it takes for the full effect of that change to take place is probably not the same as that 1/3, 1/3, 1/3. Okay, we're seeing stuff next to your camera there.
Sorry.
Your screen. Okay, so let's keep going. Here's one. Intuitively, people do not understand claims that a temperature increase of 2 or 3 degrees Celsius will be catastrophic. What are the best scientific studies showing what that will actually mean? It's funny. I don't think there's like lots of great studies on that, because, well, there's lots of individual studies showing, for example, at a certain temperature, you can have an AMOC collapse. And then what does the AMOC collapse mean? The UN did the IPCC did a study of 1.5 and what that means. And that kind of went into the dangers quite a bit. And the IPCC studies talk about 1.5 and 2 and whatever, and the increased likelihood of hitting tipping points. But I think there isn't a lot of work. There is a book that I read, but do I have it up here somewhere? It's been around for like at least 15 years, maybe 20, for Mark Lynas, Lynas, called 6 Degrees. And it's what happens at 1 degree, 2 degree, 3 degree. And this was done a long time ago, so there's a lot more information since then. But he
wrote an update. I think I still have the old book.
Yeah, did he update it? Well, I read the old one.
Yeah, he rewrote the book based on new evidence.
Okay. But the one thing we had, Kevin Anderson on our show, and by the way, we're going to have him on again, hopefully in January. But he said in 2010 that 4 degrees, what does 4 degrees mean? There you go. That's the update. I should look at the new one.
I think that's the origin, or maybe it's the update.
I don't know. Yeah. But what Kevin Anderson said, people wonder, like, what does 4 degrees mean of warming? He said 4 degrees is not compatible with an organized global community, which means you don't have functioning governments. You don't have like normal society anymore, a little more Mad Max style thing. It's devastating to the majority of ecosystems. It's beyond adaptation. Like, you're not just going to turn your air conditioner up and get by. And he also said it's not stable. in the sense that 4 degrees would lead to 5 and 5 would lead to 6. Then when he was on the show earlier this year, I asked him to update that thought, and he said, yeah, it might be that from what we know now, that number is really 3 degrees, not 4 degrees. And we're on track for 3 degrees sometime in the early part of the second half of this century, starting in 2050s through 2060 timeframe. Now, let's talk about that too, because there are other questions here about what we can do. And will we go there? Are we going to hit 4 degrees? Well, we certainly will hit 4 degrees if all we do is continue on our path of emitting fossil fuels, and our only solution to that is to talk about getting to net zero sometime. And even if we get to net zero sometime, and let's say we do it sometime 2050, 2060, 2070, okay, we actually get to net zero. If that's all we do, then I still think we hit 4 degrees. Why? Well, first of all, we continue to emit, greenhouse gases until then. And again, it's all cumulative. So it only methane goes away if you stop doing it, right? After 15 years, the man-made methane goes away. But the problem with continuing to warm the Earth is that the feedbacks, the Earth itself starts giving off greenhouse gases, methane from melting permafrost or clathrates in the Arctic Sea, or just CO2 from the soil comes out as you warm. Excuse me. And also, as Leon and Jim Hansen came up with, maybe the climate sensitivity is really 4.5 degrees, not 3 degrees. And all these numbers of 2 points will stop at 2.7 based on the Paris Accord, which I think is BS. But all that's based on a 3 degree climate sensitivity. So you throw all that into the mix, and plus, we're probably not going to be lucky, and that things will be, everything error on the side of being safer than we thought it would be. So then there'll be tipping points, as Leon is putting up here now. So throwing all that in, if all we do, and so far we're doing really nothing. We're not even reducing our emissions yet. But as we heard last week with David Hochschild, who is the chair of the California Energy Commission, California's targeting 100% renewables. We'll probably get there. And I just saw something how sodium batteries based on salt instead of lithium are now entering mass production, and they're super cheap, or they will be super cheap, and they last for 10,000 cycles or something. If it's an EV, it would last for 3.6 million miles in your EV before it dropped 20% in capacity. So, and they're going to be cheap, long lasting. And so renewables will get us there, even if we didn't have climate policy, which we don't. Well, some places do, but we would still eventually get there. But the problem is, things don't get better when you get to zero. If you're lucky, they'll stop getting worse. But because of feedbacks and tipping points and all these things, they're probably not going to get better. They're not going to just not get worse. They're going to get worse. So that leads to, what else can we do? And there's three other things we can do. One is we're going to have to adapt. And we talked about adaptation a lot. And the other thing we can do is remove CO2 from the atmosphere, called carbon dioxide removal. Very expensive, can be done, but only will be done if the government decides to pay for it, because it's not something people will just choose to do on their own. It's expensive, and you don't get anything out of it except for making the world a better place in a small amount, and everyone benefits, not just you. So you personally don't have an incentive to do it. And so we need governments to do it. But if they do, it'll scale up and it'll become a lot cheaper, just like solar panels got cheaper as they scaled up. But we're not doing that in the short run at scale. We're just basically practicing on it right now. And then the last thing we can do is to artificially cool the Earth. We know we can do it because we're doing it right now. We're doing it by accident. We're doing it because ships and coal plants and industrial plants emit the remnants of burning fossil fuels, which are sulfur, very often, a lot of sulfur. and that puts a cooling blanket around a reflective blanket around the Earth that cools it, and it's cooling by a lot, maybe around a degree Celsius, half a degree to a degree Celsius right now. No one talks about it. And by the way, it's really, and people worry about the side effects of doing solar geoengineering, putting it in the stratosphere on purpose. Well, first of all, you put about 5% as much as we're currently putting up, and people don't breathe that in. The current way we do it, which is totally by accident, kills about 8 million people a year. Not a word is mentioned about that, by the way, by anyone. Kills about 8 million people a year today, going on all the time.
Although very much from indoor air pollution, I think that kills 4 million women and children mainly a day.
Okay, you mean it's not just the fossil fuels?
I think maybe the 8 million is fossil fuels, and 4
I think 8
million
million fossil fuels is another, burning stuff indoors and like these stoves indoors.
Biomass cooking.
Biomass.
Mainly biomass cooking.
Very dangerous, yeah. So, but these things are not talked about at all, and everyone's just worried about the dangers of, we did a whole show on the trolley problem. Trolley problem simply says people care more about the deaths due to actions they take versus the deaths due to actions they don't take. And so right now, 8 million people a year dying, but like no one's responsible. It's all done by accident, so no one cares. The moment you kill like one person because you put sulfur in the stratosphere, everyone's upset, even if that ends up saving 1 million people. And anyway, that kind of answers another question why we're not doing it yet, is because people don't want to feel responsible for any changes, even though we're all responsible for the incredible changes that are happening. Very much a paradox here, and it's kind of weird, actually, right? We're causing death and destruction. We're just not doing it. Wait, by the way, we are doing it purposely. I mean, it's just a different purpose.
Yeah, not intentionally.
To have as much energy as possible and to have it as much of an advanced civilization as we possibly can. That's the purpose.
Yeah, it's a fine line between purposefully and intentionally, right? And yeah, also in a way, of course, it's a legal line. So who's legally responsible? And if you it's also a question, I don't have it here, but about geoengineering or about I think it's like we are already doing geoengineering and thing that was related to chemtrails, etc. But of course, we are emitting particles also at 10 kilometers altitude, but those are just aerosols, and those cause cloud condensation, especially when there's water vapor at that part of at that altitude in the atmosphere. And if you understand that, and you have the measurement device, and you can see the altitude of this water vapor, you see it happening. And I understand that people who don't know this, they see these stripes after airplanes, and they can make up all these conspiracy theories. But I think I think that was also the previous question. You don't have it up there anymore, but it was about if people have the what do you have it here, or can you take it back up? People have
the question about 4 degrees or what? This one?
No, if people have
understanding of claims of the temperature
intuitively, and that was the point. So I think that's people kind of think maybe intuitively that those that there's chemtrails, right? If you can your intuition, I think it's a really useful tool. As an inventor, for example, we use intuition to understand. We can think of certain technologies almost in an instant. Mm-hmm. And James Lovelock wrote about it, and I think it's really interesting how our intuition works, and we can in a way envision stuff in certain parts of our brain without thinking about it almost. But for that to work, you do need basic understanding of what's real, right? You need to understand how, for example, if you want to make a new technology using electricity, you need to understand basic you need to be able to understand electricity. You need to be, and then you can use the tools that are available to make products. But you can, and with climate as well, you need to understand the drives. You need to understand the physics at work, the chemistry at work, to be able to understand what's happening.
Okay.
And if we use that, then based on these temperature changes, then we understand that the Greenland ice sheet will reach a point where it starts melting at 2 or 3 degrees Celsius, or already at 1.5 degrees Celsius.
Oh, it's already melting. Yeah.
And so it's really based on, I think intuition is helpful, but you really have to understand. It should be based on education, of what's driving these things. And
Although I think intuition fails a bit because humans have never faced this thing before. I mean, the climate has always been, as far as we can remember, you can go back to the Ice Age, but we don't remember that. As long as we can remember, climate is this thing that varies but is relatively stable. And we've never dealt with one that is changing rapidly. And it's incredible. By the way, when I first got involved in climate change in the early 90s, I had this vision that someday, when I'm about as old as I am now, we would see the first inkling of something provable about climate change. And it would be on a graph. Like, you wouldn't even necessarily feel it, but you'd see on a graph that something due to the warming is quite different than it should have been. I was thinking that way, that the first visibility, when Hansen gave his talk, it's going to come out of the noise. I thought maybe little bits and we'll spot it somehow. I had no idea. I couldn't believe back then that such dramatic, incredible change would happen in decades, and people have no idea because it's changed an incredible amount. People pay attention to it and are not in denial, would say, my God, like the rains and the fires and the increase in hurricane strength and all that kind of stuff. And that's nothing compared to what it'll be like 20 years from now, right? Because it's not like it doesn't get linearly worse. It gets worse. Just think of water, and you have a barrier, like a wall, and the water goes up and everything's kind of fine until it gets over the wall, and then nothing's fine. And there's a lot of those kind of triggers in the not just the climate system, but in the human environment. Our sewer systems can't handle 10 inches of rain. I mean, they're not designed for that, and it'd be incredibly expensive to make them.
But 5 is fine, let's say.
Yeah, well, 5 is an incredible amount, by the way. I mean, 5 is crazy, but we're seeing.
I don't know what
15. So anyway, that's enough of a rant on that. Stacy, if you're there, turn on your camera and we'll bring you in.
I always find it interesting that indeed this talk from Hansen was in '88, and I was 0 years old at the time. I was born in '87, so indeed in my lifetime, in '88 there was a time, the point where you could see it indeed on these graphs. You could see it emerge from the noise, and some were saying that Hansen, like they're saying now, was exaggerating or was too early to make these statements. But of course, if you understand what he was saying, and you understand where he was coming from and what lines of evidence he was using, like today, he was correct, and of course that was proven by the years and decades after that. And now we're starting to see again also the evidence, but emerging much faster from what we've been saying in 2022, right? When our preprint, our paper was published, we were saying we will see this increase in the rate of warming during the next El Nino. And then in 2023, when this next El Nino happened, everyone started saying, oh, wait, maybe there is acceleration happening. And now,
of course, now they say, we knew there was acceleration all along. Our models always showed.
Yeah, some of those, some
are. Let's welcome Stacy in here.
Yeah.
Hey, Stacy.
I had a few more questions, but
hi. Yeah, I mean, there are so many questions, and
we should try to. Well, we're getting up in an hour and a half here already.
Well, the one thing I wanted to mention, it's Nevitz said it at 11:19, and I totally agree. We will all leave after this program is over and go back to our normal lives. And it's 24/7, 365 consumer and unlimited growth society, hardly a peep about climate change everywhere. And I fall victim to that myself at this time of year. And yeah, it's there's a real disconnect out there in the world.
Well,
And
not if you're with me. I'm going to talk about it.
right. And
By the way,
you were,
let's say it again. The number one thing you can do to fight climate change, unless you're going to give tons of money to research or become a climate scientist or invent a new energy storage system, do those things too. But the number one thing you can do, that's the easiest thing to do, is to talk to everyone you know about climate change. And that's your family, your friends, your work colleagues, especially your elected leaders, people you meet on the street, whatever it is. Because the reason we're not doing anything about climate change now is no one is talking about climate change. I mean, if you ask them, they're worried, and you get one-on-one with somebody, you can see that they're fearful of it, but they're not talking about it. We had the No Kings rally. We did actually have some big climate rallies in the past. And by the way, they were not covered by the media hardly at all. But there is this thing where it's like a taboo subject to some degree. And but once everyone is talking about it, that's when politicians will actually act on it, right? Until then, why are they going to do it? It's not a subject that the public cares about. Now, they should care about it because they have children and all that kind of stuff, but doesn't seem to work that way. So,
well, and I think when you ask,
everyone you know over Christmas and
I think
holiday.
when you ask people, and in the surveys it says people are concerned about climate. It's almost like well, I guess we have to be, but nobody does anything
But
about
it's
it.
not high on their list of what they vote for, right? They
Right.
vote for the economy and for racism, I guess, or something.
Yeah.
That seems to be a
I
higher
also
priority.
I have two more questions here.
All right, go ahead.
Mhm.
Yeah, which one?
Where's my
Let me turn this one off.
presentation? There it is. I think this one is for you, as you're in California. So climate news, as it said, it would be interesting to hear discussion about the increased extreme rainfall in the coastal areas around the west coast of North America, especially near Seattle. These atmospheric rivers are increasing in severity, intensity much faster than the steady temperature increase in the climate. Of course, there's no steady increase, but there's an accelerating increase, and there's this exponential function with temperature and the amount of water the atmosphere can hold. So I think that's an important point. But yeah, any thoughts for you living in this?
Although
in the direction of this, in 2 days it will hit you.
The destruction happened in Washington State, actually, not in California. We haven't had much rain here.
Yeah.
2 days.
Yeah, but it is. Yeah,
16
these things
December,
are.
Tuesday.
I mean, it's always rained, of course, and we've had heavy rains in the past. But these things are happening more often, stronger, longer lasting, and they're absolutely devastating. Again, when people like I heard like a couple of years ago, there were like 30 inches of rain in some place in Italy in 24 hours. That's absolutely insane. That's a meter of rain in a day. I mean,
That's 1,000 liters per square meter of rain.
it's just and nothing, and there is no infrastructure that can handle
And that weighs that's why I like the metric system. 1,000 millimeters per square meter is 1,000 liters, which equals 1,000 kilograms or 1 ton of mass.
Yeah,
that's a lot of, and of course it comes together.
Well,
yeah.
I think the thing that I would say about here, which I don't know, this is a question for you. And Dan, you would certainly have noticed this. I feel like our weather is changing. We've had this, we got our rains earlier than we usually do. And it's been cold. Like, I mean, it's laughable for us to call it cold compared to what winter is in most other parts of the world. But for us, it's like we've been cold for a while now. And in 25 years of living here, I don't ever remember being being this cold for this long, and this
It
early.
is supposed to be cold here. It snows even here for a very brief amount of time. It's always an
Come
exciting thing when
on.
that happens. At least where I am, I'm up on a hill, so there's a better chance of snowing sometimes every few
You
years.
get a flurry.
Yeah. But yeah, it is noticeable, and the fires. I mean, that's something never. I mean, there were always fires, but
Yes.
never the amount of the area burned is off the
Yeah.
charts. Nothing close in the past, and yeah, it's all. I think most people do notice it wherever they live, actually.
Yeah. Okay, and then this. Oh wait, no wait, this one. We'll get to this one.
Okay, I'm sorry.
Yeah, I think I don't want to go into who is referring to here, but Hugo asks, given that growth is a main driver of everything bad, is this below a conflict of interest? And I think when you talk about conflict of interest, I think it's fine if you do research, like if you publish scientific research, it's always asked if you have a conflict of interest. For example, when I was doing scientific research in Ethiopia on indoor air pollution, we were doing research on the exposure of air pollutants by women using biomass for cooking and electric stoves for cooking. And we were developing our own electric stoves. Of course, then you mentioned we personally, I could have a conflict of interest because I do research on these stoves, right? Or I develop these stoves, and we're selling these stoves once they are available. And I think that should be done everywhere in every field. When you have a conflict of interest, you should mention it. And yeah.
So what's the conflict of interest here?
Yeah, of course, it's a
The
question.
Stripe is buying carbon removal, and at the same time, they're causing emissions by supporting capitalism. Is that the idea, or what?
I don't know what that's for everyone for themselves to decide, right? If you for example have if you invest in technology or for carbon removal, and you advise that we need more carbon removal, of course that can be considered a conflict of interest.
I don't think this is a conflict of interest because Stripe is saying we want to support growth. That's our business, is to make money. And
yeah, I think there was
money, and then they do that. Also, they say we're worried about the environment, so we're going to take some of our profits and invest it in carbon dioxide removal, which, by the way, is a good thing because governments aren't spending enough on it. So the few private companies like Stripe and Microsoft, I think Microsoft spends the most, are at least getting these demonstration systems going. So the research is done on carbon removal. I mean, they're not removing incredible amounts of CO2 yet compared to what we're emitting, but at least the research is going forward, and we're learning so that when governments, if they ever decide to get serious about carbon removal, we'll have at least a couple of decades of research that we can skip, because we've done it already. But I don't see how that's conflict. I mean, you could say it's wrong for them to support growth, or any of us, by the way. But that's the way it is.
He was quoting another tweet there, but I don't think we should go in too much into a single example. I think
okay, and then maybe Stacy, do you have a few more for us?
And there was a question about acidification. I think that's also, there's acidification happening as well, and I think we should do a show on that in the future where we focus on it's a reduction in alkalinity, to be more scientifically correct, because the pH is still above 7. But yeah, of course,
it is getting more acidic. More acidic.
Yeah, exactly. So the oceans are taking up carbon dioxide or carbonic acid, as it's also called. So then the oceans become more acidic, and certain types of life, especially certain types of coral and shells and algae with shells, are more affected by this acidification than other parts of the biosphere.
Okay. So
one
Tracy.
well one a comment and a question that I saw oh, I put them in bold. Okay. Well, the question is anyone building a global climate model that takes into account, I think I ask this all the time or fairly often, all the known factors. All the current models I've looked at seem to ignore at least one really important factor. And I asked, well, what important factor? And he said, oh, it varies from at which model you're looking at. For example, aerosol forcing seems to be missing from some, effects of water vapor from others, etc.
All models are wrong, some are useful, I think, is the simple answer to that question. Yeah, I think you really you need to know what tool, what you use it. It's a tool, and then if you use the wrong tool for the wrong job, it's like you mess things up. And I think that it can be even dangerous, right? If you provide a false sense of security. I think that's happening also with in relation to the shipping emission forcing impacts, where some say that we have already seen the worst impacts. Well, we haven't, right? We see, if you look at the data, you see that there's likely much more regional and global warming in the pipeline, also from this shipping forcing change, right? From these cleaner ships. And yeah, so you really need, and that's with every model, right? If you use a weather model to try and predict the something which is not related to weather, it's not very useful, right? And yeah, so personally, when we develop new technology, for example, we know that if we build a product, the product is a better model because it has all the possible variables are inside the product, and you cannot model all these variables, right? And the problem of course, with the planet Earth is we only have one Earth, so we only have one product, let's say, to compare it to, and we can have many models, but and that's also why this inadvertent aerosol experiment from these shipping emission reductions is so useful, because then we have a real world experiment which we can compare to models and then also improve the models, because these aerosol change, the effect of aerosols are the biggest uncertainty within climate science.
Okay.
When Nadia had a question about reversing sequestration events, does that involve turning us back? Reversing those sequestration events involves turning the climate back to Cambrian, no? And then also, then she said, does reversing major sequestration events like the, pardon my pronunciation, Carboniferous and Ordovician risk unprecedented hostility to life because of increases in solar luminosity over the interim since those events?
I don't know if we can really follow that one. I'm not sure. I mean, if we do sequestration, we're going to try to bring CO2 levels back to what they were in the Holocene, closer back to 280 from 425, what they are now, or what they're going to be, 400, 500. So so we're not trying to go back to other times. Now, going back to that doesn't stop like the sea level rise, by the way. We kicked that off, and the oceans are already warm. They're already melting, the Antarctic, and so even making those changes, even using solar geoengineering to bring the average temperature down to what it was at the Holocene, which we could do. It actually won't stop sea level rise for a long, long time. It will certainly help versus not doing it, but anyway, so there's that. I want to get to another totally different kind of question that was actually asked on, I guess, Bluesky from Doomer Leo, and I don't Leau, I don't know. Okay, a great conversation, Dan. It was about something else. I asked about the possibility to decarbonize in states like mine, Pennsylvania, since we don't have a lot of sun or reliable wind, especially in winter, when we need the most energy for heating. You and your guests often say that the solutions for climate in general, or decarbonization in particular, already exist and that we are just choosing to fail. So he's basically saying, yeah, so even if we wanted to do it, we couldn't in Pennsylvania. But the premise of the question is actually incorrect. That's not true. And I did look up Denmark. Denmark is currently running on 82% renewable energy on its way to 100. And it is far more north than Pennsylvania. People don't realize New York and like Rome are on the same latitude. And so Denmark is way up there. You know, it's a mid.
Have a lot of offshore wind.
Yeah, and anyway, and they use offshore wind, but Pennsylvania can use offshore wind. There's nothing to stop Pennsylvania from doing that. You need a transmission line going across a bit of New Jersey, or you can come up.
I was going to say, I'm like, there's very little coastline in Pennsylvania.
No, but you don't need much, right? You just need to hook into the grid. And so there's many solutions, and batteries are getting super cheap, and solar is super cheap, and it actually works in the winter anyway, even though people think it doesn't, but it does. And you can, angle it so it's pointing right at the sun. And you can do all these things.
I can't imagine that Pennsylvania Power and Light is that enlightened.
No. That's a separate political question. I'm not talking about that. He's saying that in practical terms, you can't do it, and that's not true. In fact, I suggest people go take a look at our program we did with Mark Jacobson of Stanford, titled something like 100% renewables. Is it possible? And the answer is, yeah, it is. And you could do a thought experiment. Imagine if you knew in like 2 years, all the fossil fuels would be cut off, for whatever reason, political or war, whatever. Would you be able to build an energy system if you had unlimited funds? And the answer, of course you could. Now, you'd say, well, but that's unlimited funds. It can be very expensive. No, it's actually going to be cheaper because once you build the renewable energy system, you get the energy for free. And whereas fossil fuels, maybe have slightly cheaper, it's not even true anymore, but especially if it's already built, you have your power plants, and they're kind of paid for, or they're not that expensive. But every single day, you got to buy fuel for those coal or oil or natural gas, and you got to keep buying it every single day, and it's very expensive. Now, that's just the way it's priced today. If you're really being honest and you take into account the true cost of fossil fuels, you have to take into account the 8 million people a year that die from breathing in the combustion products of fossil fuels. And you have to take in all the damage of climate change now and for the next 1,000 years, by the way. It's not something that just happens for a little while. And you factor that in, and fossil fuels are the most expensive form of energy you could ever even imagine using. I mean, you couldn't even imagine a more expensive form of energy. You might as well just take $100 bills and burn them to keep warm. So, so this idea that you can't do it is just wrong. You can. Now, is it as easy in Pennsylvania as it is in California? No. California can do more. It's more straightforward, but it can be done. It will end up being cheaper, and it certainly will end up being safer. And there's many, many other benefits. Like, who wants to be dependent? We're unusual in that we can supply our own fossil fuels, but many countries can't. So their energy security is at stake. And they learned that in Europe when the Ukraine war came out. Anyway, so I just wanted to answer his question about that.
Can we keep it on 2 hours?
Yeah. This is an easy one. When will James Hansen paper on when we will hit 2 degrees be ready?
I think that was Leon's paper.
Isn't it?
That was a few years ago.
But I mean, doesn't it need an update?
He's been updating all the time, but both with other papers. Official papers as well as communications. Just search for James Hansen, Columbia University. Go to his homepage. You'll see all his papers. We cover them all the time, but both the official papers as well as these communications he does. and he talks about this stuff all the time. And we do too, but. And the answer is 2030s for 2 degrees.
And I want to thank Chuck Hinckley for his support. His super chats. I think he's saying, and I'll be interesting to hear more about that. He says that we are at 0.6 degrees Celsius, and I think that relates to degrees warming per decade.
Oh, okay.
So, yeah, I'll be interesting to hear more about how he
yeah,
got
but
to
there
that.
was this step change. Actually, Leon, there's a question for you. We had a step change. Let's say just 1 year, we just decided to lower, the sulfur content of shipping fuel by 80%. And let's ignore the earlier step. Just that one step, boom. It's a climate forcing that happens this one time. I mean, it continues at that level forever. But then feedbacks kick. So that causes warming, a little quantum of warming, and then feedbacks will kick in. If all we did, if we kept fossil fuel emissions rising at a steady pace, and the only change was this one-step aerosol, would that have like a great bit of warming in the first, let's call it 10 years, and then dribble out a little bit, like, and the acceleration rate would slow down, or does it? You see what I'm saying? Can that one step change cause continued?
So the honest answer is, and we don't know, right? And the point is there, again, those shipping emissions, those sulfur emissions, happened over the main heat sink of our planet. The oceans take up like almost all the heat.
90%.
And those sulfur emissions were only over the oceans. So those were the only direct aerosols directly being emitted over the oceans, and the altitude matters, etc. So and there's so many variables included there that it's uncertain. That's why we really need to pay close attention to what happens now, because of course, in a way, we've turned up the burner under our collective pot, right, where we're all sitting in, and so the heat goes up, and of course that is, as long as we don't change it, that's permanent. That change is permanent. So the increase in heat input is permanent. So in a way, then you could of course expect that the rate of warming will stay increased relatively to not doing that. But then, of course, how the system responds, that's quite uncertain, and that depends a bit on, especially on these clouds and this specific decadal oscillation, all these things we've already talked about today, right? And because there's all these different variables, like, for example, the Sahara dust from the blowing over the North Atlantic, that can be 100 million tons of dust, and especially during the sunny months of the year. If this dust is blowing over the North Atlantic, how much the ships emit during that time doesn't really matter that much, because it's completely masked by the amount of dust from the Sahara. But if there's very little dust from the Sahara, then how much the ship emit during these very sunny months is very important. So there is of course this natural variability which you have to take into account, so which makes it also more difficult to see what's really happening, right? Is it noise? Is it not noise? And again, there's still a lot of albedo, so reflectivity over the North Pacific, that can be reduced further if the oceans warm more. And they are warming at an extremely rapid rate. It's North Pacific. I think parts of North Pacific have warmed more in 5 years than in 170 years. The sea surface temperature increase. So that's really it's mind-boggling, right? And that's it again. That's observational data. That's not some model. That's not some extreme from me exaggeration. That's what, and everyone can look it up. It's what's really happening at the moment. So, and again, this imbalance, this net flux increase, is not decreasing; it's still increasing. So based on the observations, then I think it will keep increasing for a while, and then if that mean, and that of course that would result in more warming, especially where most of us live in the northern hemisphere, where 90% of the world population live.
Okay.
The quote or comment I was looking for, it was in regards to the video you showed, and I thought this was thoughtful. The missing word was stoicism, not optimism, not fatalism.
Okay.
I think
I
that's
saw
a
that
good
too.
that's a good way of putting it. And I thought when you said you were going to show a video that you would show the Hansen one you posted. That was
Yeah, people can
really
go on
good.
our website. We just had just a video of 3-minute video of Jim Hansen talking about climate reticence. We've talked about it here many, many times, but basically saying that this is a real problem, that climate scientists are not telling you how bad it could really be. And and I think I don't know if I shared this online or just maybe Leon when we were talking, but I had lunch with a climate scientist to talk about this issue. And this is a well-known climate scientist. I won't mention his name, but one who goes by the models more and thinks the models are right and they don't match what Hansen's saying. And we had discussions on like, well, if you're handling risk properly, you look at the worst case and you plan for that and hope for the best, but he wouldn't really go there. And I think this is what Hansen was talking about. And I think it is a real problem because Hansen gave three very specific ways and a fourth way as well of knowing that climate sensitivity is 4.5 degrees instead of 3. And you can do the math yourself on some of them. It's really not that hard. I did it. It's very straightforward. If the Earth is dimmed by 0.5 degrees in the last 25 years, as satellites show, well, there's only certain things that can cause that. One is we have less ice, reflective ice. We know how much that is. It's actually only a small piece of the puzzle there. There's the whole shipping emission things, which might be as high as Leon and Hansen say, but might be less than that. But if it's
as
less
high as the data shows, then
was that?
It's as high as the data shows. Not
Yeah. But I'm saying, but some people think that it's less looking at other data. But if that's true, as Hansen points out, well, that means the third thing is even bigger than we thought, because there's 3 components, and if there's less of one, there's more of the other. And that one is the fact that clouds, there's less clouds as the Earth warms. And we did a whole show on this with George Salutis of NASA, and definitely check out that show if you haven't seen it. It's called Global Warming, less clouds, more warming. And that's the chain, very simple. And all of them, and when you do the math, you come up with around 4.5 degrees of climate sensitivity, or more if shipping is actually less than Leon says it is. So anyway, you can do the math, and you can do it like 3 different ways, and then there's this fourth way as well. And the scientists aren't saying, oh no, he did his math wrong, or no, that's not the right formula, or no, that's not the right approach. In other words, they're not actually criticizing the science. They're just saying, well, there's lots of other studies, and this is like literally what he said. There's lots of other studies that show that climate sensitivity is less than 4.5. So even though Jim says it's 4.5, there's lots of other studies that say it's not. But okay, but that's not arguing against anything he said. You're just saying there's lots of other studies. Show me where he made a mistake in his science, and no one is doing that.
No one can.
No, that's
and
really hard to do because
they'll all
math
tell
is so
you
simple.
how great he is, how much they revere him, how much what he has done for the field.
And he's been right all
They're all
along,
on tape saying it.
Yeah.
But now suddenly
he's old, and maybe he's not. I don't know. Whatever. It's actually really weird.
Yeah.
And by the way, I think this is in some sense, and this is what Jim is trying to get out. The biggest controversy or issue in climate science today is the fact that climate scientists are ignoring this new research. Again, I'd be
Yeah.
totally satisfied if some climate scientists got together and looked at Leon and Hansen and the other people who co-wrote those papers and said, oh, no, they made a mistake here. Look, let me show you. And then, look, the science says this and boom, 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 boom. Okay. Hey, that would be good. I'd actually be happy.
I would appreciate that too.
Because what Leon and Jim are saying is that, hey, guys, it's a lot worse than you thought, you know? And if someone comes along, no, they were wrong, and here's why. You know, maybe
and the problem is, right,
you know,
it's indeed, it's very much like, okay, they don't do that, but they do publish these tweets and blogs and accuse us of accelerating.
Ad hominem.
You know, I wish we could just ignore all that because it's worthless, right? But the media.
Leon, wouldn't you be happy if someone proved you were wrong?
I very much. I always say that. I wish, and we always tell our colleagues at NASA that we hope that satellites are wrong. But you know, the media, they value a tweet or a blog by some guy as much as a scientific paper where we spend years working on and use satellite data from these billion-dollar satellite missions, right? They don't understand the difference in the value of a tweet by some crazy guy selling books or the observational data. To me, it's really, I don't understand.
Okay.
And we always say that we wish the data is wrong. We wish the science would be disproven. We publish our preprint a year before we published the final paper. Everyone was most welcome to provide the scientific rebut that showing that we were wrong, but they didn't, and they still don't. But what they did do was, on the morning our paper came out, saying we didn't include water vapor. Right? It's like these responses were completely ridiculous. You cannot make them up. But that's what they said. Like, you know, the one of the world leading scientists with 17 co-authors doesn't include water vapor, right? It's beyond ridiculous. But that's what happened. And then like you cannot really respond to those ridiculous things. But the media don't understand it. Like,
but anyway, if someone actually did take a serious look and found a serious error in what you guys did, you'd be happy, because that would mean, oh, good, we have a little more breathing room.
For sure.
So let's it's probably a good place to end it, but I'll go one more. I see this one question here, totally different thing, and I just will leave on a happier note, perhaps. Question: GDP, gross domestic product, equals energy equals CO2 emissions. Well, first of all, that's false, but in reality, don't we simply have a choice between ecological collapse or economic
They track similarly.
No, GDP does equal energy. I would go with that, but energy does not equal CO2.
It does not have to.
It certainly has. There's no question about it.
Yes.
And as GDP grows, we have been growing CO2 emissions as well. That's true. But it is possible, and certainly for electricity, it's a no-brainer, which is only 20% of the energy, by the way. It's a no-brainer to make it without CO2. Solar panels, wind, water, nuclear and other things. So you definitely can do it. Yes, you do use CO2 to make the solar panels and the wind turbines and everything like that, but it doesn't have to be that way once you've switched your energy. Now, that's only 20% is electricity, but EVs is taking 20% of transportation emissions and turning them into electricity, which again, you better supply with clean energy. Okay, now you got 40%. And now you still have heat pumps run on electricity instead of burning natural gas or oil or whatever else you're using for heat. And they work super well. They have like 300 to 500% efficiency, which makes no sense usually, but it's true, because what they're doing is they're taking the heat from the outside and bringing it inside your home, even when it's cold outside. And it's basically an air conditioner running in reverse, but that's what it is. And so heat pumps, some countries are like doing 100% subsidies for them, and they're going to have heat pumps very quickly. Other places aren't, but we could. That's the answer. We could. And then that's heating. And now you're left with about industrial emissions, cement, steel, etc. There's a number of things we can do. In the short run, we could do carbon capture on those things, which adds a little bit of cost, but would eliminate 90% of the emissions from a cement plant, for example. And then on top of that, there are new ways to make steel and cement that don't involve. Now, cement's really hard, by the way, because only half the emissions come from burning fossil fuels. The other half come just from the chemical reaction of the cement, gives off CO2. So that's why carbon capture is a really good way to do it on that. But there are ways to make these industries greener, arc furnaces, and there's all these kinds of things. So we can do it. We could start right now. We have everything we need. We could break that. Now, it does take real action, and we're not doing that. And why are we not doing that? Because the fossil fuel companies own the politicians for the most part, and the COP process as well. And so they don't have it. They don't want us to break that energy equals CO2 cycle. They want us to continue that. And so that's a political problem, but it's not a scientific problem or an engineering problem. We know how to do it. We can do it. We are doing it to some extent, and it's going to happen anyway, just for economics, but it won't happen fast enough. So we do need the political side. That's why you should talk to everyone you know about climate change. Express your fears and your concern, your optimism about solutions if we only decided to act, and those kinds of things. And also tell your friends to, well, first of all, you should like and subscribe to the podcast so that we can have it spread to more people and tell people about it. And let's see, Stacy, any?
I just want to mention, I think that it's, there was one question I got on population as well. And I think it will be useful to dissect that. And also from the perspective from a Club of Rome, of course, I think we have this formula that it's population multiplied by resource use per person, and then of course that's the impact. And yeah, you could have a very large population using very little resources, or you can have a smaller population using a lot of resources per person, right? So I think there's a saying that there's enough for everyone's need, but not enough for everyone's greed, and I think that's
I'll also say that climate change is not the only problem. There is overconsumption, which is, you can say climate change is a subset of that. There are other really big problems, the microplastics, on and on. I mean, there's lots of things happening. We're going across a lot of planetary boundaries. But at the same time, if we don't address climate change, I guess we won't have to address the other ones because it'll get us. Stacy, any final words before we head out?
Well, the one exchange I liked was, yes, well, from Brittany said, thermodynamics, 1, you can't win. 2, you can't break even. 3, you can't get out of the game. And then Nevitz responded, but with 4, but you can evolve to realize 1, 2, and 3.
Maybe. That's a good one.
Yeah.
Okay, everyone, thanks for coming. We went over our time, but that's okay. Interesting discussion. I think this is useful to do because we don't seem to have enough time during our regular programs to really cover all the questions that are out there.
And I think we got through all of them anyway.
We only got a small percentage. By the way, if you do have questions, go to our respective Twitter, X, or Bluesky sites, and you can ask questions there. I'm interacting with people all the time on that, and so is Leon. So
I changed my Bluesky to leonsimons.com.
Oh, okay. Because I think I posted you as the old one. All right. Very good.
I don't know how that works, but I changed today.
Okay, everyone. Thanks so much for coming. We'll see you next Sunday at 10 a.m. Pacific time. Everyone, take care.
Thank you all.
Bye-bye.
Bye.
Bye.